Yeah.
Thank you. Good morning. How is everybody? Hand gestures. Yeah. As far as I can tell, 4 out of 5 of the TAs have gone on strike for this class. So,
I'm guessing assignment 5 is looking like similar to assignment 4.
well, we were only ever supposed to have 4 assignments.
Sorry, the other
here.
way around. Assignment 4 is going to look the same as assignment 3.
If it exists at all, yes. Yeah. If I don't have time to put together another assignment before the end of term and reasonable enough time for you to be able to complete it, then we simply will not have an assignment 4. If we have to get rid of assignment 4, then what I will do is I will come up with 2 alternate grading schemes. One, I'll put that weight on the other assignments. The other, I'll put that weight on the exam. And whichever of the 2 of those results in a better grade for you, that's what we'll go with for those missing marks if assignment 4 cannot be for reasons that should be obvious to everyone in the room. Is this an acceptable and satisfactory solution?
Yeah.
Okay, cool. Nobody's going to file a complaint with my supervisor while I'm in the middle of a hiring process? Okay, cool.
But just to be safe, could you post their contact information? Just so, like,
Oh yeah.
we're not gonna contact them. Just like just for like curiosity.
Chair Cass at McMaster.ca is Dr. Lawford, the chair of the department. He's,
Oh, Dr. Lawford. I think I know.
Yeah, you know Dr. Lawford?
I was trying to look for research positions, and I think I sent him a couple of emails.
Yes. Yeah, he was also my PhD supervisor.
Oh, I think I was reading your paper on the earlier ones. I was looking through them, and I saw you worked with them.
Yes. Yeah, it's kind of interesting. Today's going to be perhaps a little bit of a different class because I would like to take a certain amount of time today to go off topic. Well, it's certainly related to the topic that we're going to be discussing. It turned out that one of the core algorithms that I was doing during my thesis work is the one that we're about to cover. So I thought I might take a moment and talk about my research and how that related. That may be of some general interest to the class. Is anybody interested in hearing like what actual research looks like? A few people? Okay. Enough people that I'll perform the digression. So, to review briefly, we've been talking about digraphs. Primarily, over the last, the big takeaway from our last class was that you basically don't have to make any modification whatsoever to either breadth first search or depth first search in order to apply them to a digraph as opposed to an undirected graph, which is fortunate. We also finished off with this interesting modification of the problem to the multiple shortest path problem. I think some people in the class kind of had a little bit of difficulty wrapping their head around this one, so I'll go over it in brief. In general, the problem that multiple shortest path is attempting to solve is if we have multiple entry points into a graph, which entry point will result in the shortest path to the node that we're trying to find the path to, right? Now, I was talking to a student about this just yesterday. There's kind of like a couple of different approaches to studying for this class. One is to just memorize each of the individual problems we cover in isolation, and then, like, memorize the Java code or something like that, right? I see this as a less effective way of studying. A more effective way of studying, and you may notice that this has been reflected in the most recent assignment, a more effective way to study is to understand the process of the algorithm and be able to apply it pen and paper, right? If you're able to apply the algorithm pen and paper, sure, there's the possibility of making mistakes, but your internal representation of the algorithm in your brain will be more efficient than memorizing Java code. Because if you fail to remember even one line of the Java code which you are attempting to memorize, let's just say human beings don't make good computers, right? So it's much better to memorize these things in more general terms, kind of in the same way that you would memorize the methodology for any other math problem, right? If you understand the underlying processes for something like a red-black tree, you can actually invent you can invent the algorithm on the fly, right? You don't necessarily need to memorize all 6 of the cases whereby, or I think that's 2-3 trees have 6 cases where you're inserting the node and splitting the nodes in various ways. If you understand the general rule by which all of those transformations are occurring, then you're able to create any of those transformations from the general principle that you've memorized, right? So, and I know it's like memorization at a more abstract level, but it is a more effective way to understand the material. A more effective way to understand the material on this particular slide is to understand this problem as, in this particular case, the problem is resulting from the algorithm, not the other way around, right? The observation made here is that you don't necessarily need to initialize the queue in breadth-first search with only one value, right? The question, this problem arises from the question, what happens if we populate that queue initially with multiple values? How does the algorithm behave without any modification, right? And the answer is, it will find the shortest path from any of the vertexes that the queue has been initialized with, right? That is what the algorithm will do, regardless as to our particular, situation that we want to derive from it, right? So in this particular situation, this problem of starting from multiple points and finding the shortest path to any particular point, this algorithm is derived from that slight reinterpretation of the breadth-first search, right? So, if you have memorized breadth-first search, you already know this algorithm. All you have to remember is this one detail, that if the queue starts with multiple things, you will find the shortest path among them. Does that make sense? Good? Any questions about that? Cool. Most of the algorithms that we've talked about in this class follow some general themes. And part of the, I can't remember the name of the person, but someone famous once said that education is what's left behind after everything you've learned in school that you've forgotten. And the general principles are the things that tend to stay the longest, right? You will not, like, if you have been memorizing the Java code for each of these algorithms, probably in 6 months' time you will have forgotten all of them, right? And you'll probably remember that the algorithm exists and know which textbook to look up the algorithm in, but coming to an understanding of the general principles is the point of the class, right? So, anyway. So let's talk about topologies. So, we now come to a point where we have to start talking about what these graphs are actually representing, right? When we talk about a directed graph, the arrows can mean a lot of things, right? The arrows can be physical paths through physical space. They can be things like unidirectional network connections, if such a thing can be imagined to exist. A lot of different things. One thing, which it turns out there's quite a lot of call for, is to imagine these arrows as representing precedence relationships. That is to say, if we model each of these nodes as a task, the arrows may model the order in which these tasks need to be accomplished. I'm reminded of one particular textbook which I drew the almost universal ire of the third-year class by actually constraining them to learn the textbook for this course I was teaching. It was 3MI3 programming, Principles of Programming Languages, which I am sure some of you will have the option of taking next year. I likely won't be teaching it. The textbook has, in the introductory chapters, each of the chapters of the textbook as a graph with arrows relating which chapters require material in previous chapters. So it's a dependency graph within the chapters of a textbook, which is kind of cool. But this is something that we use graphs for, right? So, a precedence-constrained scheduling problem. Given a set of jobs to be completed with precedence constraints that specify that certain jobs have to be completed before other jobs are begun, how can we schedule the jobs such that they are all completed while still respecting the constraints? For any such problem, a digraph model is useful, where a vertex is a task and an edge is a precedence constraint. However, if job X must be completed before job Y and job Y before job Z, then job Z before, and additionally job Z before job X, clearly these constraints cannot be satisfied. That is, a digraph with cycles will not have a feasible solution. Think about it in terms of definitions in a dictionary. You can model a dictionary in the same way, right? Where the definition of a word relies on the definitions of other words, right? So each definition in the dictionary has a set of, other nodes it points to if words are considered nodes. Because natural language is terrible and not nearly as wonderful in comparison to the beauty and awe and majesty that is pure mathematics, the definitions in a dictionary cannot help but include cycles, right? Because all words are defined in terms of other words. At least if you take that sort of model of human thought and language, right? The fact of the existence of dictionaries is baking in philosophical assumptions about language. But anyway, if we consider more like a, traditional computing context, if we have a series of tasks which a processor is to perform, and some of these tasks rely on the outputs of other tasks, then we also have this type of relationship. Obviously, if one task relies on another and that relies on another, there's no feasible solution to the processing of these tasks. Right? Good. So, the question then becomes, in what order do we execute these tasks? The algorithm which computes such orders is known as topological sort. Now, topological sort is not a sorting algorithm in the sense we've been studying them so far. We are not concerned that the vertices, or the values of these vertices, end up in any particular order. These have been our sorting algorithms so far. We're primarily interested in establishing an order over the keys in, some data structure, whatever, right? Okay, but I'm gonna really bake your noodle here. So, in a sense, we have been, though. If you were to take something like an array, and you were to model the values contained in that array as being nodes in a graph, and if you take the orderedness relation between the keys of the dictionary as being the arrows in the graph, then topological sort is actually the thing that we've been performing this whole time. Right? You kind of have to wrap your head around it. But that kind of brings up another important point, which is that these arrows, another thing that these arrows might represent is relations in the set theory relations context. You had a question? No? Okay. Yeah. Does that kind of make a little bit of sense? So, so topological sort, anyway. And that kind of, I realize I'm being very loose today with the lecture, but I don't know. I guess the mood I'm in today. One thing that you should really strongly understand about graphs, why graphs are so very, very important as a means of modeling algorithms. The graph maps directly onto set theory itself, where the vertexes in the graph are the elements of a set, and these arrows are relations or mappings between elements of sets, right? When you have a mapping from a set to itself, that mapping can be expressed as a directed graph, right? So, the further you go on in computer science, the more you realize that set theory really does underlie everything. That is the operational mathematical framework upon which the entire discipline has been based. So, graph algorithms allow you to work more purely in the underlying mathematics of computer science itself. So that is why graphs are important. Yeah? Okay? I don't know, I'm feeling very big picture today. So, anyway, given a digraph, we put the vertices in such an order that all the directed edges point from a vertex earlier in the order to a vertex later in the order, or report that not doing so, or report that doing so is not possible. Alternatively, topological sort is a linear ordering of its vertices, such that for every directed edge uv from a vertex u to a vertex v, u comes before v in the order, right? So, in general, the way that we will represent a topological sort of a graph is by using a linear dictionary, or a linear, not dictionary, just a linear data structure. You know, it could be a list, it could be an array. We want to linearize the thing, right? In this example here, ordering sort of begins at the bottom and travels upwards, right? This being the thing with no prerequisites, and this thing being the thing with all of the prerequisites. Make sense? Question?
Is topological order always one line, one straight line, or it can have like two elements at the same level?
Mm-hmm. So that's an excellent point. In the same way that there can be multiple depth first search trees that are correct for any particular graph, there are multiple topological sorts that may be correct for any graph as well. You can think of it, you know, you can come up with a pretty easy example of this. Wow, they really hate chalk at this institution, don't they? They actually have declared war on chalkboards. They want to eliminate all chalkboards on campus. The administration has decided this. Only in Canada can you have the decision that chalkboards are obsolete in an educational institution. My goodness. So, anyway, we can come up with a fairly easy topological sort, you know. Right? Two equivalent topological sorts would be, of course, 1, 2, 3. I'm going top to bottom because I think that makes more sense. Or, of course, 2, 1, 3. Both of these are equally valid topological sorts of that graph. So, the ordering produced by a topological sort, in general, is not uniquely defined. However, despite the fact it's not uniquely defined, you would not, like, if these were tasks being performed by a processor, following either of these orders would result in a successful batch of operations, right? The fact that there's no ordering relation between these two does not mean that, like it's not required to have ordering relations between all of the elements in a graph to produce a topological sort. Make sense? Excellent. So, at this point, I'm going to show you my thesis. Boom. So this is my thesis. There we go. So that's the short title. This is the long title. An encoding of the clock cycle semantics of blue spexus and Verilog in PBS. I put my full name in there. Because you get to do that when you're, when you got multiple middle names. But anyway, so obviously this isn't going to be on the test. I don't expect you to read my thesis for the class. But it does form an interesting it does form an interesting case study in exactly this algorithm. So, without getting too heavily into the details, BlueSpec System Verilog is a hardware description language which is modeled on a guarded action semantic. So basically, a BlueSpec description is composed of a large number of small hardware modules which all interact with each other, and the purpose of BlueSpec is to try to schedule many of these individual, they call them actions, in one clock cycle, right? Now, some of these, no, this isn't working. Okay. That would have been cool if I could use the pointer on my thesis. So, because of the way the semantics work, some actions will be blocked by other actions if they execute before them. Essentially, there's no constraint in BlueSpec preventing actions from writing to the same sets of memory elements, right? Normally, this would be called, we have a term for that, it's called a race condition, because whichever, if you have two things which are both competing to write to the same piece of memory, whoever gets there last wins, overwrites the person who was there before, right? So only one of the two will be saved. This is generally something we try to avoid like the plague, because it leads to inconsistent program states and loss of data and all kinds of nasty things. So race conditions are bad. So from a syntactic standpoint, actions in BlueSpec are not prevented from having race conditions. You can have two actions write to the same register. How that all gets shaken out is during the scheduling. So, during any particular clock cycle, if one action writes to a register, all other actions which want to write to that register are prevented from executing. Right? So, actions are modeled in my thesis work and in the compiler that I wrote that processes this stuff. Basically, the compiler takes these descriptions and forces them into a logical programming environment where you can perform formal mathematical proof over the original hardware description. It's not perfect, but some reasonable size examples work. So that's how I got my doctorate. So if you examine the scheduling algorithm itself, right, if you imagine these precedence relationships as being a directed graph, let me just find the illustration. Down. There we go. You can imagine, so this is like, you can have a graph, an undirected graph representing the conflicts between all of the various actions in a hardware module. The hardware module itself, this is what the code looks like. In case you're interested in what exotic code looks like. This example is like a simple intersection type problem. So you can model these conflicts as an undirected graph. You can then impose on that, come on. My thesis is very long. There we go. Essentially, one of the conditions that I found that was necessary to be able to produce a description that meant anything was that conflicts must be resolved by a precedence ordering in order to avoid the scheduler making arbitrary but deterministic choices about which action should precede which other action. So basically, if we have implicit and explicit rules of precedence, right? If those don't match up perfectly to the number of conflicts in the description, then it contains unresolved conflicts, and those conflicts must be resolved by the scheduler by basically it making an arbitrary selection which can't be modeled in formal mathematics. So it's actually like, in terms of my translator, anything that doesn't resolve, any description in which all the conflicts are not resolved will not, it'll fail to process. Kind of for the same reason as if you had like a circular precedence relationship. It's just an invalid graph, right? So, oh, it does work. Ha! Okay, there we go. I can't scroll though. So, basically, from there, you actually, in order to model this thing mathematically, you actually have to determine which of these actions executes first. But because the execution of subsequent actions depends on whether or not previous actions in the topological sort have been fired or not, it's not actually a linear topological sort, it ends up being a tree. And this is kind of an illustration of how the Boolean branching decisions about whether or not actions execute result in a tree representation of topological sort over all of the actions in the module. So that's how I got a doctorate. If you're interested in a more full reading of my thesis, and my brain is saying, why, God, why? It's available from the library. It's been published on MaxSphere, so you can go look it up if you really want to. But yeah, any questions? So, it's a related problem, the problem that was in my thesis, but not a, it's still a form of topological sort that was being performed, right? So, oh, and also in my thesis, I actually, as I stated, there are two precedence orderings that have to both be satisfied. So, you know, it's like you have a vertex, a set of vertices with two sets of arrows, you know, that both mean slightly different things, but anyway. So this is the type of thing that's actually a problem in reality. Yes?
I'm just wondering if that's being related to graphs. I'm just wondering what that else would be right now. So is it just any partial order set that you can topologically sort?
Oh, what are the conditions for a partial order again? Like it's, it needs to be anti-symmetric. It needs to be, So transitive, yes. Anti-symmetric, yeah, this would be anti-symmetric. It's not an equivalence relation, right? Because the one thing that throws off a topological sort, if any of these arrows are bidirectional, then topological sort is no longer possible because you have a loop of two items, right? Which is not resolvable into a topological sort, right? But yeah, yes, any partial order that's, yeah, actually, it's Dr. Macchio who's teaching that course, isn't it?
No, I think he's doing it for software and for.
Oh, okay. He was asking me whether I was teaching you guys breadth first and depth first search recently. But if he's teaching software guys, I don't know why he would be concerned about my class. I don't know. Anyway, So, all right, we need to get through more than 3 slides. Okay. So, so how might we go about actually performing a topological sort, right? Well, we can do it using depth first search. Depth first search visits each vertex exactly once. If we save the vertex given as an argument to the recursive depth first search function in a data structure, then iterate through that data structure as a stack or a queue, we see all the graph vertices in order determined by the nature of the data structure and by whether we do this, say, before or after making the recursive calls. So basically, we're going to have a list, right? The order in which we visit things during depth first search will be stored in some manner inside of that list. It turns out we have to do something slightly clever with the list in order to actually extract the topological search. But fortunately, it isn't that clever. So, 3 vertex orderings are of interest in typical applications. We have the pre-order, where all vertexes are queued before the recursive call is made. So, intuitively, we are enqueuing the vertex when we visit it, when we first visit it, right? We have post-ordering, where when we're finished processing a vertex, we put it in the queue. And then we have reverse post-order, where we perform post-order ordering. We enqueue each vertex after we're finished dealing with all of its children. And then at the end, we flip that array around. That's all that reverse post-order means. It just means post-order, then reverse it, right? So, I'm gonna spoil the ending. The reverse post-order of depth first search is topological sort, or it creates a valid topological sort. And in the same way that the depth first search produces many possible correct spanning trees, right? It will also create, it'll create one of many possible spanning trees based on the order in which vertices are named in the adjacency list, right? That same factor that produces multiple correct depth first search orderings among children also produces multiple correct topological sorts, right? It's the same factor that causes both of those. Make sense? So far, so good? Thumbs up? Okay. Good. So, for example, code. Yes. So, I think I'll do an example of this on the board. Okay, so they don't hate chalk enough to have removed the chalk brushes. Although, clearly this board hasn't been cleaned in a while. So, let's come up with a graph. I think that's acyclic, right? I think so. has to be acyclic or else it'll fail. But okay, so someone pick a node, any node. 3, good. All right. No, that's too easy. Pick it. That's already obviously the top of the search. The whole point of using the depth first search is that you get the topological sort no matter which source node you pick.
4 then, yeah.
Let's go 4, 2, 4. Well, everybody wants 4, so let's do 4. Even though it's also kind of a special case because it's like the end of the topological sort. But so, all right. So depth. Well, no, wait. We can't do that, can we?
No.
Jeez. What am I talking about? You people are leading me down bad paths. All right. So, what do the slides say about where you start then? See, this is why you need to like pick stuff that that's why you need to pick less specific examples in your textbook. All right, let's see. Where are we starting here? So this one's starting at 0. But how does it get to 3? Excuse me?
Just go to the next unmarked one?
I guess so. I mean, technically that's correct. Okay. All right. We're learning things. So let's illustrate this point somewhat then. Let's imagine we had another unconnected component. Here's the question. Where are these two nodes placed in terms of a topological sort, before or after the rest of the graph? Yes? Sorry. Depends on which vertex you start from. Well, so let's imagine that we've computed a topological sort for this part of the graph. We'll call that this block, right? We can compute a topological sort of this part of the graph. That will be that block. Does this block go before or after this one? What do you think?
Doesn't matter.
It doesn't matter. Yes. It can go here, it can go there. So what the algorithm is doing is it's going through it. So in the same way that we calculated the strongly connected components, we are going through the nodes in order, right? So, okay. So let's ignore that for the time being. Let's ignore that for the time being. So, rather than making an arbitrary decision about where to start, let's start from 0. So, depth first search on 0. Right? So, we've got two things we're pointing to. Just for the sake of argument, let's say it goes 2, then 1, right, inside of the adjacency array. So we open up DFS, I don't know why I keep doing that, DFS2, right? So we search this way. I need different colored chalk, anyway. So, DFS2 opens up DFS1, DFS1, DFS1 opens up DFS4, and we're going for a reverse post order here. So in order to generate the reverse post order, either you generate it by adding to the end and then, reverse it, or you do something clever like use a linked list and always add the new stuff to the beginning, which is, of course, what's the complexity? Complexity of adding to the head of a linked list is? Thank you. So, let's imagine that our reverse post order, although P could also stand for pre-order, it doesn't matter. So 4 ends, finds no children. So 4 is done. 4 gets added. Right? 1 finishes, is finished, gets added. Right? 2 also has no other children, is finished, gets added. 0 is finished, gets added. Right? Now, since we have our array that we're ticking things off with, 2, 3, 4, we will have ticked off 0, 1, 2, and 4. So then, the next one we call depth first search. 3, it has 2 nodes that it points to, both of which have been checked off. So it finishes and is added to the reverse post order. And is that or is that not the topological sort of that graph? Right? We can say 3, 0, 2, 1, 4. These edges are 3 goes to 0, 3 goes to 4, 0 goes to 2 and 1, 2 goes to 1, and 1 goes to 4. So, I hope that I might be able to convince you that if we started from 1, the secondary search that starts from 3 would have hit 0 and 2, and basically, rather than the enqueuing break between the 2 calls to depth first search happening here, it would have happened here instead. Right? Does that make sense? So, it's a little bit clever, right? You have to kind of think about it to understand that this is actually, like, this will work. It doesn't necessarily seem like it should work. It seems like something should get in the way of it. But it does work! So there you go. There you have it, topological search. Not the method that I used in my thesis. In my thesis, I calculated the... I traced the entire graph and calculated the maximal element and removed it from the graph and then calculated the next maximal element, and et cetera, et cetera. That's the way I did it for mine. Which, I guess I should have taken an algorithms course before I did my thesis. So, yeah. Because, like, I'm a mechatronics major, actually. I never took this class when I was doing my bachelor's degree. I took a grad level class on algorithms, but they kind of take all of this stuff as assumed knowledge, so I never actually really studied it. So I'm actually learning it along with you guys, a lot of this stuff. So anyway, it would have been more beneficial if I'd studied it earlier. Take her easy, folks.